Okay, microphone's working. So I'm going to give a talk here about a multigrid method for isogeometric thin plate discretizations. This is some work that me and my colleague Chris here, we're both in CMG lab at CU Boulder, and we've been working on this project for a little bit. So I'm going to start by introducing what a plate is and why we care about any of this. And then I'll also discuss isogeometric analysis because it's a relatively new field, and so some people are unfamiliar with it. And then I'll present some plate geometry and mechanics and how all this works, and then talk about our discretization schemes and present Schwartz methods, which we use as our smoothers for our V-cycles in Multigrid, and then present some numerical results, and then end with some concluding remarks and future directions to take this project. So what is a plate? A plate is a load-bearing structure that's in what's called plane stress. So essentially what that is we have something that's flat, and it's loaded from the top, and it will deform accordingly. So that could be things like a parking garage here. You know, cars are loaded, and the levels represent plates, the different floors. Buildings are also plates. A similar topic is a shell, which is a generalization of a plate because it has curvature. In this talk, we're going to just cover and focus on plates themselves, though. So we model plates as 2D manifolds of a 3D object. So that reduces the computational complexity because you don't have to deal with the actual 3D mesh. You just model what's called the mid-surface of your plates, and you account through thickness effects through the strain energy tensor, which we'll discuss a little later. But as with everything, there's no free lunch. So there's some difficulties associated with these plate models. So the two prevalent ones are called Kirchhoff Love and Reisner-Mindlin. And I'll give a little more details about what those models assume. But at the end of the day, Kirchhoff Love requires a global C1 continuous basis. And on top of that, it only is valid for very thin plates. Reisner-Mindlin works for a little bit thicker plates, but it suffers from what's called shear locking. And the focus of this talk is how we alleviate that effect of shear locking. And the reason we use isogeometric analysis is because our basis allows arbitrary continuity and differentiability, which makes all these things very natural. So what is isogeometric analysis? Well, it's a extension of finite element analysis where we change the basis as opposed to a Lagrange interpolating basis. We use what are called the non-uniform rational B-splines, or the NURBs. And so NURBs are pretty standard in CAD packages or computer-aided design, and they make really pretty pictures like this teapot here or this propeller blade. And what's nice about it is it allows us to do analysis on exact geometries, whereas you can imagine in the finite element setting, we throw a bunch of nodes at our geometry, and then we essentially connect the dots to create our mesh. And every time we change our geometry, we have to change the mesh accordingly. Whereas in isogeometric, the mesh is intrinsic to our geometry. So we start isogeometric analysis by defining what we call the parametric domain. And that is defined through what's called a knot vector. So we have a series of knots here, and we use what's called the Cox-de-Boer recursion relationship to elevate our polynomial basis. So you start with just these step functions, and then you use this recursive relationship to eventually go to the polynomial order of your desired basis. And this constructs our B-splines. So here's a couple examples. So the first one looks just like the typical linears you'd use in finite elements. But when you go to second order polynomials, you can see they're a bit different. They're not interpolatory, which is something to remember. And something you may notice is these knot vectors here, they define the basis of our parametric domain. And the first and last knots on both are repeated p+1 times. And what that's called is an open knot vector. And what it does is it ensures that the endpoints always interpolate. So when we're creating our geometry, we can ensure that our boundaries of our geometries are interpolated exactly by our control mesh. And also notice that our basis is globally smooth throughout our domain. So here's a picture of a 1D B-spline. So basically what we have is we have this quadratic basis, and each of these basis functions get multiplied by what's called a control point. So on the left here, this is our control polygon, which our B-spline entity will actually live inside of. And we multiply each control point by the basis, and the geometry of this B-spline inherits the properties of our basis. So for example, you can see it interpolates right here. That corresponds to this point. This right here is, we get a C0 kink in our quadratic basis, and it also interpolates right here. Okay, so on the left hand, this is our control polygon. On the right hand, this is actually shows the parameterization of our B-spline. So when you pick a point in between any of these knot intervals, so if you pick, say, 1/2, you'll live right there in the middle. And essentially what we have to construct these is the multiplication of our control points times our basis functions, and we sum them all up. Okay, and we have a very natural process of enriching the basis as well, where we can refine and preserve the parameterization exactly and our geometry exactly just by defining new control points and inserting knots into our knot vector, which will enrich our basis. And you can see if we go back between the two of them, there's just more basis vectors, but the geometry is inherently preserved. These knot intervals later will give us the notion of what an element is in isogeometric analysis. So if we want to make a surface, it's very similar. We just do a tensor product of our B-spline curves. So this is all B-splines. In the general setting of isogeometric analysis, we work with NURBs, which are non-uniform rational B-splines. Essentially what that does is allows us to create conic sections exactly like circles or parabolas. And the way we would do that is, say if we wanted to make a circle, we would create a cone, and then we slice the cone accordingly to create whatever conic section we need. So you create a n+1 dimensional B-spline and project it back down to n dimensions in order to create our NURBs. So then isogeometric analysis on these NURBs entities follows analogously to finite elements. We basically have our bilinear form, and we have some solution which takes this form here, where we have control variables times our basis functions. Okay, so let's talk a little bit about plates here. So a plate is a 2D idealization of a 3D object. So like the tables you're sitting on, the floors of this building, they're all plates because they're thin in one direction and large in two. So what we do is we model the mid-surface, which is the halfway point in between the thickness. And these two parametric coordinates, xc1 and xc2, are the in-plane coordinates. And we also have our thickness coordinate here, which is xc3. What we can do is, by defining our NURBS mapping, if we take the derivatives of the NURBS mapping with respect to these parametric coordinates, we can define basis vectors that live in plane. And that allows us to use arbitrary geometries or arbitrary contours, because now our basis vectors follow the contours that are naturally described by our geometry. Remember, we're only modeling the mid-surface, and the thickness we account through with strain energy. So we put a stiffness in our strain energy tensor that will account for any of the through thickness effects when we're deforming this geometry. So this is a crude idealization of what's the deformation modes associated with our plates, and what we'll later define as our subdomains when we're smoothing through our V-cycles. Essentially what we have up here is an undeformed plate. And so it's a little difficult to see on this projector, but the thickness there is kind of translucent, and we have the mid-surface, and then this is our normal vector. So the first displacement mode would just be translational. So we basically shift this plate down. This is just the translational effects to loading something on the top. It's a little difficult to see, but the undeformed geometry is actually right here. And we can see we've just displaced the mid-surface downwards. And then to account for rotational effects, what we do is we just do a vector component addition here. And so we add vectors to cause these planes to rotate. And so if we want to get a rotation about our xc2 direction, we just add a vector in the xc1. And if we want to get a rotation about the xc1 direction, we add a vector in the xc2. And this is what we use when we're creating our displacement profiles in plate modeling. So these two prevalent plate modeling paradigms are Kirchhoff Love and Reisner-Mindlin, which I mentioned earlier. So at the end of the day, what Kirchhoff Love says is when you deform this, if it's a thin enough plate, the surface normals that we've defined before will not skew at all. And so again, this only works if we have a very thin plate, because what's really happening is we get this shearing effect through the thickness, which causes layers through the thickness to kind of slide past each other. It's almost like if you open a book and bend a phone book, you see how things slide past each other. But as thickness tends to zero, that effect becomes less and less prevalent. until the zero thickness limit where Kirchhoff Love is actually the true state of what's occurring. So with Kirchhoff Love, we only need to track 1 degree of freedom at each node, and we basically relate the rotational displacements that we saw on the previous slide through the gradient of our translational displacements, because the rotational displacement is essentially the slope of our deformed mid-surface. Whereas in Reisner-Mindlin, we track those entities independently. We have translational displacements downward and rotational displacements tracked accordingly to what our strain energy tensor tells us. So here's our linearized strain energy tensor. It's a symmetrized gradient of this displacement profile. So what we have here is our total displacement of our plate is going to be a translational displacement downward plus some rotational displacement. And the rotational effects only are seen through the thickness. Whereas if we're at the mid-surface itself, we don't see that rotational effect occurring. We only see the translational effects. And so we take the gradient of this displacement and we project it onto our in-plane basis vectors, and that's how we get our strains accordingly. And so if you go through the differential geometry of this, our strain tensor decomposes like this. So this first term here is in-plane strains. So the alpha and beta take on 1 or 2 values. And so these are effects that are occurring in plane. Our plate assumption assumes that we don't have strains through the thickness since we've actually neglected all of those effects. And then this last term is the shear strain, which is that transverse shearing that we saw where that skews the normals as we've deformed things. So this first tensor here is the membrane strain. And so what that's telling us is how points in plane are moving relative to each other in plane. This term here is our bending strain. So this just tells us how bending affects our strain tensor. And this last term is the shear strain, which is the transverse shearing effect skewing our normals and causing rotational effects on our normals. For the plate setting though, membrane strain and bending and shear strain are all decoupled. So bending strain and shear strain are its own problem, and membrane strain is an orthogonal problem where you've loaded a plate in plane as opposed to transversely. In this talk, we only consider transversely loaded plates, so we're not even going to consider the membrane strain effects because unless you're dealing with shells, that problem is not prevalent here. So what's interesting is the shear strain term is problematic where we get shear locking. So the whole idea is as thickness tends to 0, the shearing effects become less and less prevalent. And what that means is our Reisner-Mindlin paradigm should converge to our Kirchhoff Love paradigm. In other words, our shear strain becomes 0, and in order for that to be enforced, we must have that the rotational degrees of freedom are equal to the derivatives as our translational. And this is problematic if we're using the same basis for both spaces. And the reason being is we're taking a derivative here. So if we're trying to fit linears to a piecewise constant, we're going to have a problem. The only way that's going to work is if this is identically 0 everywhere, which is shear locking in a nutshell. Essentially what that means is our shear strain tensor is absorbing all of our energy due to displacements, and we're not seeing any displacements actually occurring, which could be problematic if you're trying to design a parking garage. So this is the whole idea behind shear locking. So what we need to do to alleviate this effect is choose our basis appropriately so that this can actually hold pointwise without the locking effects. So we construct the basis functions, which this is a scalar basis function corresponding to our vertices, which on the next slide you'll see a little more what I mean by that. And this is a vector basis function which lives on the edges of our control mesh. What we want to do is preserve what's called the plate cohomology. And so we want the gradient operator to map our basis functions from our translational displacements to our rotational displacements. In addition, we need some projection operator that will map our infinite dimensional problem to a finite dimensional finite element space. So if we can design our basis functions like this, we can satisfy our locking-free methodology at every level of discretization, which the reason we could never do this with multigrid before is because at coarse grids, we would encounter locking and we would not have the ability to smooth appropriately and get an accurate and reliable solution on the coarser grids until you've refined your mesh to alleviate the locking effect. So with the B-spline basis, all of this is very natural. these right here show what our basis functions will look like. So if we consider the vertex basis function, which lives right at that point, the gradient of this basis function can be represented with vector basis functions that live along this edge and along this edge. There's also two other vector basis functions which would live along this edge and this edge. I just haven't showed them here. So what we observe is we have a bicubic B-spline. If we take the gradient of this, what we should have is, if we're taking the gradient, the first component of our gradient would have a quadratic in xc1, but a cubic in xc2, whereas the second component would have a quadratic in xc2 and a cubic in xc1. And so you can see the support of the basis functions has shrunk, which is what happens when you take derivatives of B-splines. So with this, our weak formulation can be unified between the Kirchhoff Love and Reisner-Mindlin plates. So our Kirchhoff Love plate, what we do is we take the gradient of our displacement profile and put it into our bending energy. The Reisner-Mindlin plate, we have our two displacements here, and we have this extra shear strain energy. And together with all this, this is what we'll use to implement our isogeometric methodology. So we define our translational and rotational displacement spaces. Through here we have homogeneous Dirichlet boundary conditions, which are just essentially what's called a weakly clamped plate. So what that means is on the boundary we cannot displace vertically and we cannot rotate along the boundary, but we still have the freedom to rotate into the center of our domain. And so again, this unifies our framework because now we don't have two finite element spaces depending on if you're using Kirchhoff Love or Reisner-Mindlin. We can just design these spaces so that those are consistent with each other. And so our variables we're solving for will be just displacements if we're using Kirchhoff Love. If we're using Reisner-Mindlin, we have displacements as well as rotations because we need the 3 degrees of freedom as opposed to 1. So now since shear locking is no longer an issue, we can devise a multigrid scheme so that this all works. And so we use Schwartz methods because we can choose our subdomains so that we can have the translational and rotational degrees of freedom communicate with each other freely. So here's an example of our subdomain. So if this is our control mesh, if we look at one smaller part of the subdomain, we have our vertex, basis functions, and our edges, and this right here defines our subdomain. In a more formal framework, what we have is one of our vertex subdomains is just the support of our vertex basis function. And then our rotational subdomains, or the rotational basis functions that live in these subdomains have support that is contained entirely in our vertex basis functions. And so we consider two different smoothers here. We have additive Schwartz and multiplicative Schwartz. So additive Schwartz is analogous to Jacobi. It's kind of an attractive option because it is parallelizable. Multiplicative Schwartz is analogous to Gauss-Seidel, which is not quite as parallelizable. Additive Schwartz doesn't preserve partition of unity normally, so it's typically used as a preconditioner, but if we add this relaxation parameter, we can actually make it converge. These terms here are V, are actually our restriction and prolongation operators, which restrict our subdomains, which restrict our total domain to just the subdomains we've defined on the last slide. So the Schwartz methods with these overlapping subdomains kind of recast this problem so that instead of it being one big plate, we have a bunch of these small plates that we're modeling, and their boundary data is given by the coupling with their neighboring plates. So here's some numerical results. We consider 3 problems here. The first is just going to be a uniformly loaded square plate. The second will be this parallelogram plate. And the third is kind of interesting. It's the Grand Canyon skywalk. So if you've ever been to the Grand Canyon, I have a good picture of it later. It's basically a glass plate that you walk out and you're looking straight down into the Grand Canyon. Better hope that thing's not going to break. So the first numerical results I'm going to present are Kirchhoff Love. So it doesn't suffer from shear locking, so all we need to do is show that this converges independently of our degrees of freedom. So this problem actually has an exact solution, just the uniformly loaded square plate. And you can see that our convergence factors are really great. A number of e-cycles to smooth this out. It's completely invariant of how many degrees of freedom we actually have in the system. And so if we run an FMG cycle on here, you can see it converges at the rate we expect. And it's a second order convergence rate. We have a little bit of at the beginning, the hiccups when you start this process. But as you continue down, it smooths out, levels out, becomes second order, what we'd expect. So for the Kirchhoff Love parallelogram plate, we actually have a singular solution. So the convergence is slowed, but it still converges nonetheless to our solutions. And so this doesn't have an exact solution, so our way of testing the convergence was by how many V cycles it takes to reduce the residual norm by 10 to the 6th. So here's the Grand Canyon Skywalk. You have that glass plate, and so we are going to neglect all of these primary structures, which are the beams, and just look at the glass plate itself, because that's the only part we can reliably model as a plate. This is what it looks like, and it's kind of nice because in isogeometric analysis, this ability to model circles exactly is native to the paradigm itself. And you can see we have excellent convergence factors, and the number of V cycles with respect to degrees of freedom is fairly invariant. And again, there's not an exact solution to the Skywalk problem, so we use the 6th order of magnitude reduction in residuals as our figure of merit. So now for Reisner-Mindlin, this is the tricky one because it suffers from the shear locking. So the numerical method that we presented claims that that's no longer a problem. So we just want to show that as we vary thickness, it converges. And so here's a big table. Each one of these sections is thinner and thinner. So right here is a very thin plate, and you can see pretty much across the board we have very consistent convergence factors and number of V cycles required. And that was using multiplicative Schwartz. Additive Schwartz is shown here. So we have a very thin plate again. The reason we consider additive Schwartz is for the parallelizability. And so these are the smoothing factors we needed. There's not really a way to pick these. You just have to find one that works. The larger it is, the slower or the faster it will converge. The smaller it is, the more likely it is to converge. It just so happened that down here we had to lower the smoothing factor in order to get it to converge. But other than that, it's fairly consistent across the board. So in conclusion, we presented a unified theory between Reisner-Mindlin and Kirchhoff Love that's locking free and allows us to use a multigrid method to find solutions. And our numerical results confirm the theories that we presented. I want to extend the work to more intricate geometries, so even crazier skywalk type problems. And I also want to extend this to shells, which have curvature. And so you'd have to do some tricky things like pick your subdomains to limit the amount of curvature per element on our courses meshed, because there's other locking modes present in shells. So I want to thank John Evans, who's my advisor, and CMG Lab, which is a lab I work at CU. And I also want to thank the conference for giving me the chance to talk and present my research.